Hi everyone, my name is Audrey Berlin and I'm a PhD student at the University of Utah. Today I'm going to be talking to you about iron's pressure, temperature, and strain rate dependent deformation mechanisms. So there are a few goals for the study. The first was to compile experimental deformation results across pressure, temperature, and strain rate space. The second step is to model these experimental results in EVPSC in order to determine the deformation mechanisms. And the third is to systematically describe how iron deforms across pressure, temperature, and strain rate space. For instance, if we change the temperature by X degrees, what will this do to the deformation mechanism? And the fourth goal is to constrain extrapolations to geologic strain rates. For instance, if I want to know what happens to iron deforming in the inner core, I'd have to extrapolate to extremely slow strain rates and extremely high temperatures and pressures. So it would be good to constrain those extrapolations. I'm going to do a brief overview of a deformation experiment method. So here I've shown a radial diamond anvil cell. This is not the only deformation device that exists. This could be a shock experiment or a multi-anvil experiment or a gas gun experiment. But whatever it is, we're going to have some synchrotron X-ray source that is going to show us in situ what is happening during compression, give us some diffraction images, and we'll fit them in MOD, the soft right field refinement software, and this will give us a lot of data that we have to work with. And the data that we like to focus on is texture and lattice strain, which can only be measured in radial geometry. So lattice strain is the strain calculated from interplanar spacings measured at high pressure and at 1 atmosphere by diffraction method. And this is not equal to the macroscopic strain in the same direction. Lattice strain is given by it's a function of the shear modulus and uniaxial stress of the material. And as for texture, this refers to the crystallographic preferred orientation of your sample, and this happens when grains orient themselves in a particular direction under certain conditions. And we like to show texture on an inverse pole figure, which shows the probability that a given crystallographic plane is oriented normal to compression direction. So that's what this triangle looking thing is. And the scale bar is in multiples of random distribution. So this is a probability. As for EVPSC, that is the Los Alamos code for the elastic viscoplastic self-consistent method. And I'm just showing you what's happened for one experiment that I've modeled. So ideally, I'll have as many experiments modeled as possible under a variety of different pressure, temperature, strain rate, deformation conditions. And so what I'm going to do for each experiment is look at texture and try to simulate that. So I've got my example here on the top left. You can see I've matched the maxima and the scale pretty well. And we're going to look at lattice strain. So here we just want the order and magnitude and shape of these curves to match between the experiment and the simulation, and I got it pretty close here. And third, we're going to look at the slip system activity in EVPSC, and this will let us know the dominant deformation mechanism. Here you can see that system 1 is at 60% activity, and system 1 is that purple line. This is basal slip. So that's going to be your dominant deformation mechanism for this experiment. And this experiment was conducted at 17 GPa and 600 K at a strain rate of 0.5 times 10 to the minus 5 inverse seconds in a D-dia. So for next steps, we're going to look at all of the other experiments that I can find, model them, and then make a deformation mechanism map across pressure, temperature, and strain rate space. That's just a little bit of what I've been up to lately. Thank you for listening. You can contact me at my email here. And that's it.